So today we're getting to what I think is sort of the end of a lot of hard work. The first half of the semester we put a lot of effort into giving ourselves a bunch of building blocks for building digital systems. And then recently we've been talking about an instruction set for a computer and trying to convince ourselves that we had all the instructions that were necessary to compile high-level programs, high-level language programs into machine code. And I think with the conclusion of sort of doing procedure call and return and getting all the conventions straight about who saves what registers and where arguments go and things like that, we're finally all set to actually say, okay, we have an instruction set. We want to implement it. So, here we are at sort of one of the, I think, the highlights of the course where we're finally going to put all these separate storylines together and work on a circuit diagram for a computer today. Whenever you're doing a digital design, you have to think a little bit about what your goals are. And in addition to functionality, in other words, achieving, making sure in our particular case that we can execute all the different instructions in our instruction set, that the hardware has all the capabilities needed to do that, we also might want to ask ourselves some questions about what other goals would a design achieve. And the typical sort of conversation that happens in engineering teams, we first talk about, trying to build something that has high performance. And sometimes the goal is just the best performance possible. If you're into sort of the supercomputer game, every time you can make your computer faster by a factor of 2, you're really pleased with yourself and you move up higher in the rankings and more people buy your machines. In a different dimension, and this is becoming increasingly important, is sort of minimal cost. As we embed computers in pretty much every component, particularly electrical components that have any sort of functionality, some sort of sequencing they have to go through, and whether it's washing machines or refrigerators or desktop computers or satellites we're sending out of the solar system, those all require some amount of intelligent control, the control that reacts to sensor data and controls the actuators correctly. And often, particularly if we're trying to computerize a light switch or something like that, we'd be very interested in doing that at absolutely minimal cost. We don't want to have our interface of a device, of a component to the digital world to be very costly. So we're hoping to spend, on the order of maybe cents even in trying to make that happen. And then finally, there's sort of the middle ground, and that's the ground we'll be taking today. And in fact, we'll be spending most of our time just making sure we have the functionality correct. When designing, in particular, a digital system that emulates in hardware a computer instruction set, here's the sort of the pieces of the formula that go into determining the computer's performance. So, we're going to measure the performance of the machine in terms of the number of instructions per second that it completes. So, nowadays the sort of computers that we have, in our pocket probably are several hundred million instructions per second they can complete. And then sitting in front of us in our laptop, maybe a billion or 2 instructions per second that it can complete. And maybe in a supercomputer center, several times that. Some nowadays with these fancy graphics cards that have hundreds and hundreds of functional units in them, they may be completing a billion or not a billion, a trillion or 2 instructions per second, mostly through parallelism. So our goal here is to sort of say, look, first of all, we're going to design a machine that will execute 1 instruction every clock cycle. In other words, the machine will have some registers in it that hold the state. And so it's a sort of our typical diagram of some logic and some state registers. And we're going to clock those registers at some rate. And every time we do rising edge of a clock, will mark the end of the current instruction and the beginning of the next instruction. So we're going to design a machine that does 1 instruction every clock cycle. And we're able to do that because we have a very simple instruction set, a reduced instruction set computer. That's what the beta is, a RISC machine. And then we're going to try to get the best performance as possible, although we're not going to spend a lot of time on that today. Right at the end of the course, we'll come back and we'll talk about increasing the clock rate by taking our big, single stage pipeline stage, a single sort of or fancy finite state machine with logic and a set of registers, and worry about pipelining it so we can get the throughput up. And the machines that you have in front of you in your laptops, have a 20-some-odd stage pipeline that they're executing instructions in. So their clock rate is, about 20 times what they'd be able to achieve if they didn't use the pipeline at all. And that's part what makes your computer so fast.